Okay, so good evening, students. So, welcome back to our session on the topic applications of derivatives. So, yeah, Tara and Shyam are here. So, good evening. So, we'll just wait for a few minutes, guys, so that remaining students can also join the class. Right, so meanwhile, if you have any doubts, any questions, so please text me in the text box so that I can reply you. So, Max, most probably today will be the last session on topic applications of derivatives. So, as part of this typical derivatives and all, we are left with one more topic, that is our continuity and differentiability. So, some part of this continuity and all we have discussed while we are actually dealing with the topic of limits. So yeah, so for this continuity and differentiability, we can say it's quite related to our limits as well as our derivatives part of it. So that we'll be seeing after the topic of applications of derivatives. Right? Yeah, Keshwan also here. So we'll just see. So previously, if we talk about our applications of derivatives, so we have focused mostly on our rate of measure, and we have even covered the concept of approximation. So in our previous session, we have actually started with our tangent and normal part of it. So today we'll be continuing that, and we'll be doing few quite number of questions in that context of tangent and normal. And once we are done with tangent and normal, we'll be seeing one more thing, the next topic, and that will be our last topic in the applications of derivatives. Right? So yeah, Shyam has raised a question. So asked a question in which topic and which question you are talking about. Okay, only 3 of you are here. I don't know what happened with others. About differentiation. Okay, I don't know what question exactly you asked me. So can you just take a pic of your question and send it to me so that I can even in this lecture, or else if time permits, do one thing. At last of the class, you can just take a picture of it and send it to me. And in the next session, I'll just clarify your doubt. Right. So then I think only 3 of you are here. I am not sure whether we can start or we can wait for 2-3 minutes. Okay, meanwhile, we'll just have a quick overview of our session. Yeah. So, in the previous session, as I already told you, we have discussed about rate of measure, and I clearly mentioned this topic is actually important, right? And we have done word problems also in the next contest. So, the next topic we have done is approximation, right? So, for approximation, what we have to do is by seeing the question itself, you have to take the function, right? In some questions, they might give you the function f of x. In some questions, they might not, right? So, it depends upon the question. You have to take the function f of x, and then you have to proceed and solve the given question and find the approximate value for the given question, right? And coming to our today's topic, so we are going to start with tangent. That is nothing but equation of tangent. We can say length of the tangent will also be part of it, right? So in terms of tangent, we'll be dealing with two typical topics. One is the equation of tangent. If you guys remember, I have even discussed about this equation of tangent in our previous session. So, but we'll be going through once again. So, in this, we'll be seeing equation of tangent and we'll be seeing the length of tangent. Same for the normal also. So, we'll be seeing the equation of it and then we'll be seeing the length of the normal. So, when we coming into this tangent and normal, we'll be having one more concept of subtangent and subnormal. So, if you guys remember, I have clearly explained this subtangent and subnormal topic while we are doing with our 3D geometry, right? So, if you guys remember, I have explained you. If not, again, in our 12th standard, we are having our 3D geometry topic. So, there it will be coming again, once again. So, once again, we'll be talking about the subtangent and subnormal concept in our 3D geometry of our 12th section. And the next topic will be angle of intersection of two curves. And I already told you it will be a typical formula like finding the angle between two lines. Here they have mentioned as curves. It can be lines also. So we have seen the formula of tan theta is equal to m1 plus m2 by 1 minus m1 m2. Isn't it? So it's a typical formula, the same here. But in terms of differentiation, how it is related means our m1 and m2 are nothing but our slopes. So our slope can be represented in terms of derivative, right? So that's why even this angle of intersection will also coming into our applications of derivatives, right? And last but not the least, so the last topic of our applications of derivatives is nothing but increasing and decreasing functions. Right, so for this increasing and decreasing functions, majorly what we have to understand is we have to check the conditions. So we have to thorough with the conditions. If once we are actually thorough with the conditions, then it is easy to find whether the given function is increasing function or decreasing function. So now you might have a question like what is an increasing function and what is a decreasing function. Some of you might have known the difference between these two. Some of you may not. So, while we are discussing this topic, I'll start with what is an increasing function, how the graph it will be, and what is an decreasing function, and then only I'll be jumping into the conditions for these two increasing and decreasing functions. So, yeah. So, these are all the applications of derivatives. So, these are the 6 concepts which will be coming under the applications of derivatives. So, where the first two are we have already covered. So, let's get started with our today's session. As I told you, we'll be starting with the tangent. So, if you guys remember equation of tangent. So, how we will be writing 2-point equation? I asked you in the previous session, you told me y minus y1 will be equal to m into x minus x1, where our m here in terms of derivatives, m is nothing but equal to dy by dx at the point x1 comma y1. Right, so we are simply substituting here. Then our equation of tangent will become as y minus y1 will be equal to, in place of m, we'll be substituting this, that is dy by dx at the point x1 comma y1 into x minus x1. Right. So the reason behind why it is necessary, so instead of finding the slope, we can directly, so because they have already given the curve here, so you can directly find the derivative of the curve and then you can easily find the equation of the tangent with respect to our derivative of the given function y. Right, so we have seen the equation of tangent. So let's solve a question in regard of this topic. So here is the question. So if the tangent of the curve, so for every question I'll be giving you few minutes so that you can think of it, you can start solving it and then I'll let you know how to solve it if you are not getting it. Yeah, so just take your time, 2 to 3 minutes and read out the question and write the information what and all given and what you have understood from the given question. Sorry, here it should be alpha square. So this should be alpha square plus beta square. So here there is a correction in the question, that is alpha square plus beta square will be 61, not a square plus b square. So just take a note of it. Alpha square plus beta square will be equal to 61 and you have to find the value a. So just take your time, 2 minutes and just give it a try. So first, what's the question they have given here? If the tangent of the curve. So the tangent of this curve at point a comma a cuts off intercepts alpha and beta on the coordinate axis. So if we are having x by a plus y by b is equal to 1, then what are the intercepts? Intercepts a are nothing but a and b. Right. So first the condition is we have to find the equation of tangent. So first let us find the equation of tangent. So to write the equation of tangent, what's required here? Slope. So the given curve here is 2y cube is equal to ax square plus x cube. So let's differentiate it. So 2 into 3y square and dy by dx is equal to 2ax plus 3x square. So from here my slope dy by dx will be equal to 2ax plus 3x square by 6y square. Here I have mentioned tangent will be at the point a comma a. So we have to find slope at the point a comma a. So let's substitute that. So it will be 2a square plus 3a square by 6a square. So here it will be 5a square by 6a square, which is nothing but 5 by 6. So we end up getting the slope of the curve is nothing but equal to 5 by 6. Right. So until now you are clear with it. So we got the slope is equal to 5 by 6. So let's write the equation of tangent. So how we will be writing the equation of tangent? So y minus a is equal to 5 by 6 x minus a. So simplify it. So 6y minus 6a is equal to 5x minus 5a. So we can take x terms together and x and y terms one side of the equation and remaining to the other side. So here 5x minus 5y. So if I bring 5a here, so it will become minus a here. Right, so to eliminate minus a, I will be dividing the whole expression by minus a. So it will become 5x by minus a minus 5y by minus a is equal to 1. So here 5x by minus a. So here it will become plus 5y by a is equal to 1. So in terms of intercept form, your equation will be standard form will be x plus a by y plus b is equal to 1. So this is the standard form of equation for intercept form. So we have to reduce this in such a way. So here it will be x by minus a by 5 plus y by, sorry, y here is 6, right? Sorry, here it should be 6y. Sorry. So 6y is 6y. So here it will be 6y, sorry, 6 will be coming here. So a by 6 is equal to 1. So after converting our tangent equation in terms of intercept form, we end up having x by minus a by 5 plus y by a by 6 is equal to 1. So hence our intercepts here are minus a by 5 and a by 6. So our alpha will be equal to minus a by 5 and beta will be equal to a by 6. And they have given one more condition, that is, as I told you, here it should be alpha square plus beta square is equal to 61. So now you can substitute that alpha and beta in that equation so that we end up having our a value. So alpha square plus beta square is 61. So alpha is minus a by 5 whole square plus beta is a by 6 whole square is equal to 61. So here a square by 25 plus a square by 36 is equal to 61. So here it will be a square will be equal to 25 into 36 and 36 plus 25 will be 61. So both will be getting cancelled. So it will be 25 into 36. So a will be 5 into 6, which is equal to 30. So hence the value of a is nothing but equal to 30. So now I think you guys are clear. Yeah, Shyam. Yeah, I got it. I have seen it. So 6y, I just entered it wrong. So now here we have to find the value of a. So here the value of a is nothing but equal to 30. Right? So I think you guys are clear with this question. So if you have any doubts, please let me know. So this is how. So now you have understood, without, if we doesn't have 2 points, then we can't directly find the slope. Right? But if we are having the equation of the curve, using our derivatives, we can find the slope. Right? So yeah, I think you guys got the answer here. So moving on to the next one, the equation of normal. The same thing, so we have even discussed about the equation of normal. So the difference between tangent and normal will be, these two are two perpendicular lines. So if m1 is our tangent of, slope of tangent, m2 is slope of normal, then the product will be equal to minus 1. So that's why here the slope will be minus 1 by dy by dx. Right, so I have explained you this equation in the previous session. So let's solve a question for normal also. Yeah, so I have explained the question for tangent. So now I think you can solve this question. So try and solve this question and let me know what's the answer. So here you can understand. So you have to find the distance between the normal of this curve and the origin. So here the normal of this curve will be at point whose abscissa is 0. So in our geometry, 3D geometry in your previous class, you have learned what is abscissa and what is ordinate. So abscissa is nothing but your x coordinate and ordinate is nothing but your y coordinate. Right. So yeah, just give it a try and let me know what's the answer here. Okay. Has anyone solved it? At least let me know what's the point, like at what point we exactly finding the normal. Because here they haven't given the complete point, but they have mentioned only the abscissa of the point. So what guys, have you got the answer here? I think you might have solved it. Not it? Okay, I'll just quickly give you a hint at least here. So here what they have mentioned, find out the distance between the origin and the normal to the curve at a point whose abscissa is 0. So first point is we have to find the normal of this curve. Right, so before that, to find the normal of the curve, we should know the point. So here they mentioned the point whose abscissa is 0, which means x is 0, but we doesn't know y. But we know the curve here, y equal to e power 2x plus x square. So substitute your x0 here. which means e power 0 plus 0. So e power 0 will be 1. So y will be, yeah, I'm just solving it, Tara. Just look at here. So they mentioned abscissa is 0. So if abscissa is 0, they are talking about the curve. So substitute the x value in the curve. You end up having your y value that is equal to 1. Right. So hence you got your point, that is 0, 1. So this is the first point. We have to find out the point. So once we got the point, our next aim is to find the equation of the normal to this curve. So to find the equation, what we have to know? We should be aware of the slope. So the point here is 0, 1. So let's find out the slope here. That means dy by dx is equal to e power x will be e power x into 2 plus 2x. Right. So at the point 0, 1, so x will be 0. So 2 into e power 0 plus 0, which is equal to 2. So here if you observe, the slope we are getting for this particular curve at the point 0, 1 is nothing but 2. So now let's write the equation of our normal, that is y minus y1 here is 1, which is equal to minus 1 by 2, because it's a normal. They are not talking about tangent. They are here talking about normal. So here it will be x minus 0. So just cross multiply, 2y minus 2 is equal to minus x. So x plus 2y minus 2 is equal to 0. So this will be our equation of the normal. So now it's not at end. So we have to find the distance between the origin and the normal. So what's our formula for distance between origin and normal? So it will be, we can do the perpendicular distance. So it will be modulus of 0 x0 plus 2 into y1 minus 2 by root over coefficient of x will be 1, so 1 square, and coefficient of y will be 2, so 2 square. So which is equal to 0 plus 2 minus 2 is nothing but, I am getting 0 here. So 2y plus x minus 2 is equal to 0. So now here we have to find the distance from the origin. Sorry, I have taken the point 0, 1. So we have to find from origin. So this will also be 0. Sorry, we have to find the distance not from this point 0, 1. We have to find from the point origin. So 0, this will be 0, this will be 0. So minus 2. So modulus minus 2 by 1 plus 4 under root, which is equal to 2 by root 5. So hence the distance of the origin from the normal of this curve is nothing but equal to 2 by root 5 units. Right. So here it's like we have to find more number of things here, more number of things, so that we end up getting our answer. So first we have to find out the point, and then we have to find out the slope, and then we have to write the equation of the normal. So once we are having the equation of the normal, then we have to find the distance between the origin and the normal. That is nothing but our answer, final answer, which is equal to 2 by root 5. Yeah. So 2 by root 5, correct. So I think you're clear with this question. I think yes. Okay, if you are clear, we can move ahead to our next topic, that is length of tangent and length of subtangent. So let me show you. So this is the figure where our tangent, so P and T, so this is some curve here, and this PT is the tangent where the length of the tangent will be PT. So if this length of the tangent will be PT and this tangent is making angle psi with respect to the positive x-axis, then the formula for length of the tangent is nothing but y root over 1 plus cot square psi. Right. So our cot square psi can be represented in terms of dy by dx. So here our formula will be for length of tangent, that will be equal to y into root over 1 plus dy by dx whole square by dy by dx. So how we actually converted this? So our slope dy by dx we know that is nothing but equal to our tan psi. Isn't it? So in place of cot, how we will be converting? So here if you observe, I'll just explain you this. So cot square psi. So if I want to convert this, what I'll do? 1 plus 1 by tan square psi under root. So now if I have to take LCM, then it will become tan square psi plus 1 by tan square psi under root. Right. So under root 1 plus tan square psi will be as it is under root, and tan square psi, if root is there, we can directly write that as tan psi. So we know that our tan psi is nothing but equal to dy by dx. So in place of tan square x, we can substitute our dy by dx. So hence it has been converted into this format. So 1 plus, in place of tan square psi, we have substituted dy by dx whole square, and in the denominator we are having tan psi, that is nothing but dy by dx. In the same way, for every equation we have converted by considering our tan psi is nothing but dy by dx. Right. So hence the length of the tangent here is nothing but equal to y root over 1 plus cot square psi in our normal angle terms. But in terms of derivatives, if we try to find it, so it will be equal to y root over 1 plus dy by dx whole square divided by dy by dx. Right. So I think you are clear with this. In the same way, it will be the formula will be given for our length of subtangent, length of subtangent, length of so length of tangent, length of subtangent, length of normal, and length of subnormal. For each and everything, we will be having the same typical format here. Right. So here the only thing you have to remember is, if you are aware of these formulas, that is y root over 1 plus cot square psi and mp cot psi and all. So if you are aware of this, you can easily convert into tan form, and in place of tan, you can substitute your first derivative dy by dx. So we'll just see the formulas for length of normal and length of subnormal. Right. So here the length of normal is gp. So the g in this figure you can see gp is nothing but length of normal, and mg is nothing but length of subnormal. Right. So you will be seeing this typical thing again. Like we have already seen, I guess, how we get this formula in our 3D geometry. If not, don't worry, we'll be again covering this in our 3D geometry chapter. There we will be discussing the length of tangent, length of normal, length of subnormal, and all those things. But as of now, for applications of derivatives, you have to remember that in tan psi, we will be substituting our dy by dx, and such a way that our lengths of normal, subnormal, and tangent and subnormal will be converting into our normal derivative form. Right. So here you can see the length of normal, the general formula here is mp secant psi. So how can we convert this? So secant psi can be written as y root over 1 plus tan square psi. Right. So mp is nothing but, here they have assumed it should be y. So it will be y. So secant phi. So we are having secant square psi minus tan square psi is equal to 1. So from here our secant square psi will be equal to 1 plus tan square psi, and our secant psi will be equal to root over 1 plus tan square psi. Right. So that's what we have substituted here. So in place of secant psi, we have substituted root over 1 plus tan square psi, and again in place of tan psi, we have substituted. So in place of tan psi, we have substituted dy by dx. Right. So that will be our length of normal. In the similar way, our length of subnormal will also be substituted. So our general formula for length of subnormal is mp tan psi. Mp is nothing but y, they have assumed in the figure, and tan psi can be written as dy by dx. Right. So these are the four concepts: length of tangent, length of subtangent, length of normal, and length of subnormal. So now you can try and solve this question. for the parabola y square equal to 16x, the ratio of the length of subtangent to the abscissa is. So you have to find the ratio. So just think over it. And how can you solve it? So just take your formula from your previous slide. What is the formula they're asking? Length of the subtangent. So let's see what is the length of the subtangent here. So the length of the subtangent here is y by dy by dx. So they are talking about length of subtangent. So I will be writing here. So length of subtangent is nothing but modulus of y by dy by dx. So you have to find the ratio of length of subtangent to the abscissa. So just give it a try for this question. It will be very easy. Just it will be some logic will be there. So if you get that logic, then it's done. Have you got anything? At least you might have got the length of the subtangent. Is it 2xy? Are you talking about the ratio? How can be ratio 2xy, or else are you talking about the length of the subtangent? Shyam? Are you talking about the length of the subtangent? So this is the formula for our length of the subtangent, isn't it? So y by dy by dx. So here you have to find dy by dx itself. So y square is equal to 16x. So 2y dy by dx will be equal to 16. So from here dy by dx is nothing but 16 by 2y, which is equal to 8 by y. So the slope here, no, length of the subtangent, it will not be 2xy. So can you just check? So from where there will not be an x term. So if you observe the dy by dx for the given curve y square is equal to 16x is nothing but equal to 8 by y. I guess you might have done something wrong here. Check it, Shyam. So yeah, so if we substitute here y by 8 by y, then it will be y square by 8. So the length of the tangent here we end up having y square by 8. But here the question is we have to find the ratio of length of the tangent with respect to the abscissa. Abscissa will be in terms of x. So can we convert our length of the tangent in terms of x? So if you observe in the given curve y square is nothing but equal to 16x. So in place of y square by 8, so in place of y square we can substitute 16x. So 16x by 8, so it will be 2x. Right, so in terms of x, our length of subtangent is nothing but 2x. So length of subtangent is to abscissa, which is equal to 2x is to x, and x and will get cancelled. That is nothing but 2 is to 1. So the ratio here of the subtangent with respect to the abscissa is nothing but equal to 2 is to 1. I think you guys are clear with this. So can you just let me know if you have any doubts in this question? So if you have any doubt in this question, please let me know. If you are clear with it, please let me know so that we can proceed further. Okay, got it. So what about others? Okay, clear. So we'll just move ahead. So there is one more question, two more questions. So before solving these two, we'll just finish our further topics and then we'll get back to those questions. If not, we can take them as a homework. So as I told you, angle of intersection of two curves. That is nothing but in simple way we can say angle between any two lines or any two curves. So if we are having two curves, so with respect to those two curves, we have drawn two tangents. So the angle between those two tangents is nothing but our angle between those two intersecting curves. So we have already derived this in your 11th standard. So why we have taken this here in the sense, so how can we relate this with respect to our derivatives? So as we know, tan psi will be equal to the formula here, m1 minus m2 by 1 plus m1 m2. So the only thing we have to remember here is the change will be m1 will be dy by dx of curve 1 and m2 will be the dy by dx of curve 2. Right. So instead of finding the slopes with respect to the points and all, if we directly have the equations of the curves, so using the equations of the curves also, we can find the slope so that it results in the angle of intersection of those two typical curves. Right. So the only point you have to understand here is, in place of m1, it will be the substitution of dy by dx of curve c1, and for m2, it will be the substitution of dy by dx of curve c2. Right. So let's get into our next topic, that is our increasing and decreasing functions. Right. So if we are having an open interval, so we are having a real function. Right. So if any function which is given here, when we can say that the function is either increasing or decreasing or strictly increasing or strictly decreasing. So here we are having four conditions, but generally we will follow with strictly increasing and strictly decreasing conditions. So what are the conditions here? So here if you observe, if we are having x1 less than x2, so x1 less than x2, which implies, so if x1 less than x2, then it implies f of x1 less than equal to. So if it is less than equal to f of x2, then that function will be increasing. Here if it is less than equal to, if it's simply less than, then it will be strictly increasing. Right. So here we are having a condition, if our x1 less than x2, then our f of x1 is less than equal to f of x2. So if it is less than equal to, then it's simply increasing. But if it is simply less than, then it will be strictly increasing. So that function is called to be a strictly increasing function. The same way for decreasing and strictly decreasing. So if we are having x1 less than x2, if this implies our f of x1 is greater than equal to f of x2. So whenever you are having this equal to, you can say it's simply decreasing or increasing. Right. So if not, our f of x1 is only greater than f of x2, then we can say it's strictly decreasing. Which means if we doesn't have that equal to, then we can say it is either, if it is less than, then it will be strictly increasing. If it is greater than, then it will be strictly decreasing function. Right. So let's see the graphical representation. So here in this graph, if you observe the first graph, until this part, it is increasing, the graph is increasing, but here it is decreasing. Again it is increasing. So here it's a slight, here also there is an increase of the, sorry, it's not decrease, it's also increase of the function, but the shape is actually changing here. It's not following a regular path. So this typical function, we can say it's a increasing function. Here if you observe, there is no cut, no cut in this curve. It's simply going like this. There is no distraction in middle. So these typical curves are called to be strictly increasing function. And the same way for decreasing function as well as strictly decreasing. So here if you observe, here it has decreased and again some change here. Again decrease, some change and decrease. So it's a decreasing function but not strictly decreasing. Right. Strictly decreasing in the sense there should not be any alter in the graph or the curve. It should not be any disturbance. But here if you observe, it's going like a step kind of thing. Right, so that's why this function is called to be increasing function. This is strictly increasing function and this is decreasing function. And the next is strictly decreasing function and neither increasing nor decreasing function. So strictly decreasing, the same definition. So there is no cut, no disturbance here. So it's simply decreasing like this. So this function is called to be strictly decreasing function. And here the last and final graph, if you observe, this is neither increasing nor decreasing, because if you see, it's going like a same constant graph. It's not increasing like this and it's not decreasing like this. So this typical graphical representation is called to be neither increasing nor decreasing function. So these are the typical 5 graphical representations of our increasing and decreasing functions context. Right. So yeah. So now let's solve a question. I have given you a condition. So here what they have meant. So you have to show that the given function f of x is equal to 7x minus 3 is strictly increasing. So you have to show that it is strictly increasing. So how we will be following this? You have to take the condition of strictly increasing and then you have to solve it. So just give it a try. How can you solve this? Which means we have to assume that if x1 is less than x2, we have to start with this. So this is our starting condition. This should result such a way that our f of x1 is also less than f of x2. Then we can say this function is strictly increasing. So how you can prove that? So let me solve this. So here the starting condition is same. So x1 less than x2. So what is the function here? 7x minus 3. So I am multiplying with 7 on both sides. So 7x1 less than 7x2. So by multiplying with a positive number, there is no change in the inequality. So now I am subtracting minus 3 on both sides. So 7x1 minus 3 less than 7x2 minus 3. So by subtracting any number on both sides also, there will not be any change in the inequality. So these are the properties of inequalities. So now if you observe, 7x1 minus 3 is nothing but f of x1 less than 7x2 minus 3 is nothing but f of x2. Right. So hence from this condition x1 less than x2, we end up having the conclusion that is f of x1 is also less than f of x2. Right. So hence we can say that the given function f of x is strictly increasing on this interval R. Right. So I think you guys are clear with this question. So please let me know if you are having any doubts. I think you are clear with it. Okay. So in some cases what it will happen is, so if we even start with x1 less than x1 less than x2, if I have multiplied with negative number, that means if my function I am multiplying with minus 7x on both sides, then my inequality will be greater than, because while multiplying with a negative number, my inequality will be changing. Right, so then it won't give you the less than condition, then we can't prove it. Right, so this is how it goes. So you have to here apply the rules of inequalities and follow it. Right. So we'll move to the next part. So this is the basic increasing and decreasing function, and with respect to our normal x and y values, how we can say whether the function is increasing or decreasing. So how can it relate to our differentiation? So the condition with respect to our derivative is the function f is strictly increasing in the interval a comma b if the f dash x is greater than 0. Right. If we got the f dash x is greater than 0, then we can say it is strictly increasing. So if we got our f dash x is greater than equal to 0, then we can say it is only increasing function. Right. So that will be our third point here. So if our f dash x is greater than and equal to. So if whenever we are having this equal to, then we can say that function is increasing. Right, so here the second point is f is strictly decreasing if f dash x is less than 0. If it is only f dash x less than 0, then we can say it is strictly decreasing. So the opposite of it, if f dash x is less than equal to 0, then I can say it is decreasing function. Right, so whenever we are adding, we are having this equal to here, then we can say the function is either increasing or decreasing. If not, we are having only greater than or equal to, then we can, if we are having greater than or less than, then the function will be either strictly increasing or strictly decreasing. So with respect to our differentiation, to find whether the function is an increasing function or decreasing function, we have to find the f dash x and verify whether it is greater than 0 or less than 0 or greater than equal to 0 or less than equal to 0. So you will be understanding this by solving questions only. So let's see this question. So what they have given in the question, show that the function f given by f of x, so f of x is equal to x cube minus 3x square plus 4x. So the f of x is equal to x cube minus 3x square plus 4x. So you have to, here x belongs to R. So you have to show that this function is strictly increasing. So how can you show this given function is strictly increasing or not? So use your derivatives here. Just now I have shown you the conditions. So just think of it. And see how can you solve this. So here they have mentioned it should be strictly increasing. So which state that it should be satisfying the condition, that is our f dash x should be greater than 0. So you have to check whether your f dash x will be always greater than 0 or not. So if it is greater than 0, then you can say the function is strictly increasing. If it is greater than equal to, then the function will be only increasing. So check. First thing is you have to find the f dash x here. Okay. I think you guys are clear with the concept. So let's solve this question. Has anyone solved this? So at least you might have found out the f dash x. So here the function is f of x given. So we have to show that this function is strictly increasing. So the condition we are having for strictly increasing is nothing but our f dash x should be greater than 0. So first let us find out f dash x. So f dash x will be equal to 3x square minus 6x plus 4. So by seeing it directly here, we can't say whether it is greater than 0 or equal to 0 or less than 0. Right, because our x value can take any real value. So let's rearrange these terms. So if I take 3x square minus 6x, if I have written 4 as 3 plus 1, then it will be 3 I can take common, which will be x square minus 2x plus 1 plus 1. Right, so I have rearranged my terms such a way that 3 into x square minus 2x plus 1. So now further my x square minus 2x plus 1 can be written as x minus 1 whole square plus 1. So I have rewritten my f dash x such a way that it can be written as 3 into x minus 1 whole square plus 1. So if you substitute any x value here, so even if this term becomes 0, we'll be having this plus 1 term, which means the minimum value of our f dash x is 1, which means our f dash x is greater than 0. So that's what we have to prove. So hence we have proved our f dash x is greater than 0. So we can say our given function f of x is strictly increasing on the interval r. Right. So this is how we have to check by converting or rewriting the f dash x and check whether it is greater than 0, equal to 0 or less than 0. Right. So this is how we will be solving these typical questions of increasing and decreasing functions in terms of our derivatives. Right. So this is all about our applications of derivatives. I think you guys are clear with this question. Yeah, got it. So solved. Okay. Yeah, strictly increasing. So you already proved it. Good. So yeah, so this is all about our applications of derivatives. So I'll be just giving 2 questions as homework. Just work it on. So yeah, I'll just give you 2 questions. So just take a note of this question. So find out the length of the normal to the curve. So here you have to find the length of the normal to the curve. So this is one question. Take this as homework. And the next question is this. So take this also as homework. So this is related to length of the subtangent. Right. So these 2 questions you can work it on. Take it as homework. So this is all about our applications of derivatives. So as the concept of derivatives, so we have finished our methods of differentiation and then we have even finished our applications part of it. So we are left with a small topic, that is our continuity and differentiability. So that I'll be covering in our next session. So yeah, so that's all for our applications of derivatives. So yeah, Sham, you said you having some doubts. So please just send me the picture of it so that I can answer your question. So yeah, so that's all about our applications of derivatives part. So in our next session, we'll be starting with the topic of continuity and differentiability. So thank you guys.